Hello everyone and welcome back again to another video on calculus. In this video we'll be looking at U-substitution as an integration technique. So as usual we'll start with a section on theory, which will be longer for this video, and then we will move on to exercises where we will solve a few integrals through U-substitution. This method is very common for solving integrals along with integration by parts and trigonometric substitution, which is quite similar. So yes, a pretty important section. It's good to have a solid foundation in order to be well enough prepared to learn U-substitution, and yeah, it's very useful. So let's get into it. The first thing we do after we see this classic integral of a function dx that we have to find, the first thing we do is choose a function u, and u is a function of x, okay? So you see f of x, and then based on that, you yourself choose a new function u of x. Now, you might be wondering how to choose what your u function should be, and it's hard to explain, but theoretically, but with practice, you'll get used to picking the appropriate function, u. So after you've chosen your function u, you have to evaluate u dashed of x, which is essentially du by dx. And then you'll have an equation like something like this, and then you have to solve for dx. And you express dx as a functional of u dashed of x and du. So, as you surely know, if a equals b over c, then c is equal to b over a. And that's what you can do here. You can switch the places of these two, and then you'll get dx equals to du over u dashed of x. Okay, so this is a step that you'll have to do every time, pretty much. And then remember, our original integral has a dx in it. So what we're going to do is replace this dx in our starting problem by this expression du over u dashed of x, since they're equal. Okay, so substitute this into the original integral. So then the problem becomes the integral of f of x times 1 over u dashed of x du. So this is the same as this. We've just rewritten dx in this form. Okay. The problem is that the integrand, which is this function inside of the integral, can only contain one variable. And as you'll notice here, we have a function of x and u. So that's not okay. And the way we can deal with that is that any leftover x, or x's, can be rewritten in terms of u by looking at the x-u relationship. So essentially what that means is if, for example, u equals, let's say, 2x, and then we have an x left over in the integral, we have to rewrite it in terms of u. Well, how do we do that? We can just say that x is equal to u over 2. So we just replace any x's by u over 2. But yeah, we'll go more into detail in the application section. Okay, so here we have an example before moving on to, say, the other exercises. This is an example that I've worked through in detail. So consider the integral of 2x plus 1 over x squared plus x plus 1. Oh, here I've forgotten the dx, which should be there. So here we are going to let u equals to x squared plus x plus 1. Remember, this is our choice. We have chosen u to be x squared plus x plus 1. You can choose u to be any function of x. But the reason why this is a good choice for u will become apparent later. So, of course, we compute du by dx. That's the next step. We differentiate term by term. X squared becomes 2x. And the derivative of x is 1. And the constant just differentiates to 0, so we can ignore it. And then we do this little trick with exchanging the positions of these two. We get that dx equals to du over 2x plus 1. Okay? And this 2x plus 1 is essentially your u dashed of x. Okay? So, why was this a good U-substitution? Because the problem now becomes 2x plus 1 over u times du over 2x plus 1. And the 2x plus 1's can cancel out. And that's a perfect way to get rid of all the x's, because we can only have one variable in the integral. Now, why is this correct? Well, we have the 2x plus 1 from before. X squared plus x plus 1 is just u, so we replace it by u over here. And then we replace dx by du over 2x plus 1 using this relation. And yeah, neatly, all the x's are gone. So we're just left with the integral of 1 over u du. Oh, sorry. And of course, you can just pretend these are x's. When you integrate, you get the natural logarithm of the absolute value of u plus an integration constant. Okay, so essentially when you have the integral of a of x over b of x, a sort of ratio of function like this, what you can try to do is that if you notice that b dashed of x is a of x, right, then you can substitute u equals to b of x, and then all the x's will cancel out nicely, as was shown in this example. Now, of course, there are plenty of other forms for the integral of f of x. Can be anything, so it's hard to know directly what U-substitution to make or whether to even use U-substitution. But this knowledge will just come with practice. So just practice a lot of U-substitution exercises, and then it'll come pretty easy. So the goal of this video is just to show you what U-substitution is, so that you get a general basic understanding of it, and then you can practice, do practice problems by yourself later on. Yeah, so the goal is often to cancel factors containing x out, like we have done. Yeah. And remember, once we get to the form ln of absolute value of u plus c, this answer is in terms of u. However, the original exercise was an integral in terms of x. And the integral of a function of x dx will always be another function of x, not u. So what we have to do now is transform this answer, this expression, ln of u plus c, back in terms of x. And this step is usually quite easy. It's just replacing. So since u is equal to x squared plus x plus 1, we can just directly substitute that. So our answer becomes the ln of x squared plus x plus 1 in absolute value, and then plus c. And that is the solution to the integral. Okay, let's move on to exercises. So for the first integral, we can substitute u equals to 2x plus 1. Then du by dx is going to be 2, differentiating term by term. So dx equals to 1/2 du. So the integral becomes, one integral of 1 over u, and then dx is 1/2 du. So we can bring the 1/2 out front. We get 1/2 integrating 1 over u du gives us ln, and then it's going to be ln of u plus c. And then we will just replace u by what we defined it to be, 2x plus 1. So our final answer is going to be 1/2 ln of 2x plus 1 plus c. There we go. Next question. Cosine of 2x. Yes, you can probably just guess what the answer is by guessing functions which differentiate to this, but let's do it properly by substituting u equals 2x, and then dx is going to be 1/2 du. Yes. Yeah. I've skipped the step, but essentially you can double check. This is correct if u is 2x. So this becomes integral of cosine of u with a factor of 1/2 du. And the integral of cosine is going to be sine. So we get 1/2 sine u plus c. And then for a final answer, we're just going to replace this u by the 2x. So our answer is going to be 1/2 sine of 2x plus c. There we go. Okay. Whenever you have a sine of something, or a cosine of something, or tangent of something, or a square root of something, whatever you have in here, it's often a good idea to see what would happen if you tried to substitute u equal to whatever is inside of these functions, for example. It could also be ln of something. You could try substituting u to be whatever is inside that function. It won't always work, but it's a good try. Things will often cancel out that way. Okay. 1 over x squared plus 2x plus 1. Now, here you should notice that if you just substitute u equals to x squared plus 2x plus 1, then du by dx is going to be 2x plus 2. And this is going to be left over because we don't have a 2x plus 2 on the numerator, which to cancel it out with. So this is not going to be a good idea. I just tried it to show you what would happen. Instead, we should factorize this because we have a perfect square on the denominator, and then we can rewrite it as something to the power of -2. And then this is going to be a linear expression, whatever's inside here. So we can just make that u. And du will be equal to dx, which is always nice. So I'll show you how things work out. We can rewrite it as 1 over, or directly even, x plus 1 to the power of -2 dx. And then whenever you have a linear function, so that would be anything of, or yeah, so not just linear, but whenever you have something like x plus a constant, basically, then if you say u is equal to x plus some constant, then du by dx will always be equal to 1, meaning that du is equal to dx, which is really, really nice. So that is the case for us here. We can just say u equals x plus 1. So du will be equal to dx. So this just becomes the integral of u to the power of -2 du, because dx and du are equal. And then integrating will give us -1 over u, I believe. Yes, plus c. So then we just we just replace u by x plus 1. So this becomes -1 over x plus 1 plus c. Okay. Next one. Square root of 3x minus 1. So again, this is a perfect example confirming the rule, for this case at least, that when you have the square root of something, you should make u equal to whatever is here. So let's do that. We'll say u equals to 3x minus 1. Then du by dx will be 3. So dx equals to du over 3. And we can bring this factor of a third out front. So we're going to get 1/3 integral of the square root of u du. And the square root we can rewrite as a power of 1/2. So then what do? We add 1 to the power, giving us 3 over 2. So that comes, we're going to get 1/2. When we multiply by 3 over 2 here, these cancel out and we're left with 1/2. So we get 1/2 times 3 over 2, 2/3, u to the power of 2/3. Is it? Let's see if this works. No, 3/2. So no, 2/3. Wait a minute. We have to add 1, so yeah, it will be 3/2, and then 3/2. So maybe here I should have 2. Is it 2 over 9? Yeah, perhaps it's 2 over 9 here, plus c. So let's see if we differentiate whether it will work out. We get 2 over 9 times 3 over 2 times u to the power of 1/2. And then these cancel out. 3 over 9 is 1/3 u to the power of 1/2. Okay, it works out. Yeah, sorry, I don't know why this took so long. But 2 over 9 times u to the power of 3 over 2 should be the correct integrated form. And of course u to the power of 3 over 2 is the same thing as the square root of u cubed. Okay, so let's write that down with the u replaced by 3x minus 1. So we're going to get 2 over 9 times square root 3x minus 1 cubed. Plus c. Okay, there we go. Next question. X to the power of 19 over, and then we have a product. So you should be recognizing the form a plus b times a minus b. We have that here, and if we were to expand that, you'd get a squared minus b squared, which with our numbers is x to the power of 20 minus 1. And yeah, you should always, whenever you see either, if you see a squared minus b squared, you should think what would happen if I factorized. And if you see the factorized form, you should think what would happen if I expand. Can that help me in any way? So always think about that. Like we did here, we have an expanded perfect square. Think about factorizing it and see if that helps you in any way. So in this case, it does. Because if we just rewrite the denominator in this difference of two squares form, and technically we have one squared here, which is just 1. And then if we set this to be u, the denominator, then so u equals that. Du by dx is going to be 20 x to the power of 19. And minus 1 is just a constant, so we can ignore it. And this works out perfectly because we can cancel out this x to the power of 19 on top, essentially. So dx is going to be 1 over 20 x to the power of 19 du. Okay, so the entire integral becomes x to the power of 19 over u times the dx is going to be 1 over 20 times the x to the power of 19 du. Obviously the x to the power of 19s cancel out, that's the whole point. And we're left with 1 over 20. We can bring the constant multiple out to the front. And then integrating 1 over u du gives us the ln of the absolute value of u plus c. And then we're just going to take this and replace u by x. So we get 1 over 20. 1 over 20 natural logarithm, and then we have u. Well, u equals to x to the power of 20 minus 1. So that's also equal to x to the power of 10 minus 1 times x to the power of 10 plus 1. So now that you're substituting u by its x expression, you can choose whether to write this or this form. They're both fine because they're equal. Personally, I'm going to go for x to the power of 20 minus 1 because it's shorter to write, but it's up to you. So ln of that in absolute value plus c, of course. Okay, and we should be done with that integral. Yeah, sometimes when you have an ln of an absolute value, you can just write it as ln and then with brackets if whatever you have here is always positive. Right? But in this case, it isn't always positive, so we have to keep the absolute values. But yeah, as a side note, if in here you have a function that's always positive, it's probably better to replace the absolute value by brackets. And the absolute value comes from the domain of the ln function. So if you have f of x equals to ln of x, then x has to be more than 0. Okay. Next one is e to the power of 5x plus 3. What we can do here is rewrite this as e cubed times the integral of e to the power of 5x, right, by exponent rules, and then e cubed is just a constant multiple. We only have e and 3, both constants, no x's. Dx, of course, we're going to say u equals 5x, and dx is going to be 1 over 5 du. So we're going to get e cubed over 5 e to the power of, I'm already integrating, it's going to be e to the power of u, but then we replace u by 5x plus c. Yeah. So essentially, more simply, we can rewrite this as e to the power of 5x plus 3 over 5 plus c. So as you get more comfortable with this U-substitution method, you can even skip steps and just go fast on these easier exercises. Okay, so this next one, with the square root of 1 minus x squared, it's actually a pretty complicated integral. Generally, you'd solve this with trigonometric substitution, which we haven't covered yet, but we will. You say x equals to sine of an angle, for example, phi. I was planning on solving it with U-substitution as well by saying u equals arc sine of x, which is essentially the same thing, and then working with U-substitution. But it's probably better to introduce this integral in the trigonometric substitution video. So we'll save that for later and ignore it for now. It is a famous integral, and we will spend quite a lot of time on it when we do trigonometric substitution